Cool, looks like we're going. So been looking at some of the deeper stuff recently. I kind of want to have a look at Ethclient now. So when you've got your node running, it gives a RPC server. So you can send commands to it while it sits on the network and does its thing with all the peers and maintains the blockchain. It also makes this server that you can send commands to tell it to do things. And this is useful when you want to actually put transactions on there rather than just listen. And also when you want to query the blockchain. So the way that Bitcoin kind of asks you to do it is with Web3. And they make the console, which actually utilizes this, a JavaScript console, and they also put in this framework so you can run a JavaScript script that can access all the things that your node is doing. So you run Geth on the side, and then you spin up a script that tells the script where the node is running, and then using that you can do things like get the Coinbase or get a balance of Coinbase is an address in this case, but then you can get the balance of the Coinbase. And it really is just like when you want to talk to your node and tell it to do things, you have to send it commands, and it mostly utilizes this, and this is almost a go-to way of communicating with Geth. But for people who don't want to use JavaScript, they've also built in this Ethclient, which is, from my understanding, very similar. And there's a I've got a start. There's Go programming. Yeah, Ethereum development with Go. This book kind of explains a lot on it. But essentially, instead of using Web3 within a JavaScript context, you use Go, and you ask for this Ethclient. It gives you access to pretty much all of the stuff you want to do with the node. So I've been playing with this a little bit. I obviously want to get pretty good at this because in the end I think the goal is to be able to make your own scripts and programs and servers that listen to the blockchain and then do actions after it sits there reading them. Cool. So here we are in Geth and going to Ethclient, and there's not many files in here, and even the test is tiny, and all it does is set up a heap of variables, and if they fail, it'll spit an error, I guess. Yeah. Cool. So all this really does is it spins up all these things and they pass the client, and if it spits an error, then it fails, really. There's a signer, which I don't really understand what it's doing. It says it's implementing types.signer. So if we go up to core types, I'm assuming there's a signer in here. and it's going to have an interface maybe. Sig cache, sign transaction, sender, signer interface, yeah. So encapsulates transaction signature handling. This is not a stable API, may change, but needs a sender, a signature value, a hash, and an equal. And then they've made this one, which is a structure that just has an address, a block hash, and then it implements two of them, equal and sender, and spits an error for the other two. So I think I'm not fully sure why they use this at the moment. I haven't dug into it. I think a signer is something that wraps around a transaction, or you pass it a transaction and it can sign. Yeah. Not sure at all. Hash equal. Or it wraps a transaction and gets the sender and stuff. Anyway, cool. Unimportant to programming Ethclient. Anyway, so that's quite small. So that. And then in Ethclient itself, 500 lines, and seems pretty reasonable to go through this in detail and know all the stuff that it's doing. So we've got this client structure, and it's just wrapping an RPC client. So what does RPC client do? Represents connection to an RPC server. You can write to the connection with a writer, and handles all the connection channels. So it would just be like, if it shuts down on you, or some of these will be ticked, some of them won't. Or if it reconnects, or if it's getting errors, it just stores them there. But it mainly gives you this write connection, which is a net connection, and that just gives you it's the same as a file. If you write stuff to a file in any programming language, you can write it the same way to these net connections, and that's just the way they design it. So it's all really similar, and same sort of program can write over the net if it can write it to a file, really. So the client, they got dial, which gives you a dial context, and it takes a raw URL. So in here you can see this is what they're doing: client error, Ethclient dial Infura. Infura is a service that provides a node, so you don't have to run your own. So you don't have to run Geth and talk to it via RPC. You can have these guys, they're running the node. And I think it's pretty common for anyone who's not really, because nodes are hard to run. They're huge and expensive. So if you don't want to do that, but you still want to program and have stuff that talks to the blockchain, you can use these services. And Infura is one about it. So Infura gives you a web API to talk to. And that's what he's doing here. It's passing that web address, which is a raw URL. That URL doesn't have to be a web address. It can also be your local host information, or it can be this IPC file, and the RPC client handles all those under the hood. And the difference is nothing really. Like, in the end, when you're programming, inter-process communication is just writing to a file that both programs are listening to. Over the internet, it's a URL, but the net connection makes it a file. So all these things are writing to what essentially are files, in the same way that if you spin up a script that just reads a text document and writes to a text document, it does the exact same thing. Just the structure of the text is a little bit different. So the main one is calling dial. You pass it a raw URL. It calls dial context, which is right here. Context at background, it creates a blank context. I don't understand context at all. But it's something you pass when you're doing requests, or you're sharing across processes. And then if it gets shut down, you use this as the common thing to talk between the processes, I believe. I don't fully understand it. They don't even really require you to. When you call dial, it makes this blank new context.background and passes it around. They got this dial context, which is actually taking that. But then essentially here is them calling RPC dial context, which is the back end, I guess. And if we're over here in RPC, it's going to be dial context. And this does the same thing. So Ethclient really just wraps these two. This takes WebSockets, standard in and out, and IPC, and it'll handle whatever URL you pass it. So back here, calls dial context. It gets the actual client, passes it into this new client structure, which just wraps it. So now you got a client, or it's called as rpc.new with nothing. It's taking the URL, and you got this client structure you can play with. Gives you a close, so it closes a connection. Blockchain access. So there looks like to be a function called getBlock. Pass it a context, and what I imagine is a function call. I think this would probably match up to whatever the RPC functions that have been made are. Then they give some nice helper functions to say you go client.blockByHash, you pass it a hash, and then it calls this getBlock with that and the parameters. And then blockByNumber does the same thing, but it's got a different. So whatever EC getBlock does, which is here, this looks like it's going to have a big bulk of everything in it. Yeah, it looks like 100-ish lines. Yeah, not even close. 60 lines within a 500-line document, so it's 10% of the file is this function. So it's pretty important. We'll go back to that. Header by hash. Goes and it gets the call context. Call context, context, get blocks by hash. error, and they pass it heads. So they call get blocks by hash, and this returns a header as well, but they disregard the cool. So that's going to be under the RPC client. That function needs to be dug into. Same thing here, header by number, they call in C call context. They got an RPC transaction extra info structure. And then this RPC transaction unmarshals JSON. So this, I believe, is when you get a response from the server. It comes back as JSON. So you send, like, you're essentially making a JSON file that you're sending to the node. That's what RPC is. And when it comes back, it is also in JSON, so you're going to have to read that, I guess. And this is just setting up the way to do that. So you got a RPC transaction, unmarshal JSON, takes a message. So yeah, you've got so you're going to make a new RPC transaction. You're going to have this message, which is an array of bytes, which I think would be a receipt from the server. So something's come back from you. And you're reading it into the structure. It's got a transaction, it's got a TX extra info, which has a block number, a block hash, and who it's from. And they don't use it straight away, I believe. Transactions by hash. So you find a transaction with the given hash. So it calls the context, get transaction by hash. So that's another. This is pretty much just wrapping everything that gets sent to the node, because the node takes care of all the brains. All you're doing is you're making the function call in a format you can understand. So they send call context JSON, and what I imagine is unmarshalling the JSON into here, I believe. I don't see it right now, but you've got if error does not equal nil, else if JSON equals nil, else if R equals nil, they return the transaction without it. So this is all error checking. If JSON from does not equal nil and JSON block hash does not equal nil, does not equal nil, block hash does not equal nil, set sender from server. So they call this with the JSON transaction, JSON from JSON block hash. So that is probably the key. Set sender from server. I think that's actually in the signer, isn't it? Yeah, here it is. So they pass it, it makes a types.sender, sender from server address and block. Address block, transaction. Types sender. Okay. So if you make a sender file structure, it needs to have a types.signer in it, and they just make this sender from server a really lightweight types.signer, because you don't actually really need to do much when you're doing this stuff. You don't check the signer really, whereas a node would be checking everything that the signer is doing. Transaction sender returns the sender address of the given transaction. So if you pass it a transaction, it gives you the sender in a common.address. Transaction sender, transaction block. The transaction must be known to the remote node and included in the blockchain at the given block and index. So you have to tell it, if you go to transaction and you give it a block hash, it gives you the sender's address. Why would that be useful? Don't know. And this is kind of the conclusion I'm coming to slowly, is that most of the stuff they're doing here isn't super useful if you want to program a script. It's mostly if you want to make transactions and put them onto a server. I might be wrong, and there's a whole book dedicated to it, which I plan to go through. But right now, all it's doing is building blocks from scratch, really, and sending them to the node. Transaction count returns the number of transactions in a given block. Takes a block hash. Transaction in block returns a single transaction at the index in a given block. Let's go and call context. Call context again. Transaction receipt returns a receipt of a transaction. To block arg number, takes a big int and returns hex util encode big number. To block num arg. So what does that do? Common hex util encode big. Encodes big int as a hex string. To block arg number argument. None of these take strings, so which is kind of confusing me. So why would you need to convert your big int into a hex string at this point? I don't know, maybe it's below. RPC progress, starting block, current block, highest block, pooled states, known states. Sync progress retrieves the current progress of the sync algorithm. And it returns Ethereum sync process. Isn't this sync process? That's a... who knows? Raw message. Call context eth.syncing. Get it back. Unmarshal into raw. JSON raw message. Progress equals progress. JSON unmarshal raw at progress. So they call context, puts it into raw message. decode raw message into syncing, decode raw message into progress. And then they build this sync progress structure. Which looks exactly the same as this, but this is RPC progress, whereas this is sync progress. Not sure right now. Cool. Moving on. Subscribe new head. Subscribes to notifications about the current blockchain head on the given channel. New heads. So you get notifications, I'd imagine, every time there's a new blockchain header. State access. Network ID returns the network ID. So it'd be number 1 if it's a main chain, number 2 if it's number 2 doesn't exist, but 3 and 4 are test nets, for example. Version is an integer. Call context into version, net version. If version set string ver10 does not equal OK, decimal, version dot set string ver, so it returns it into a ver string. So this version integer you can set from a string. Yeah, cool. Balance at returns the way balance of the given account. The block number can be nil, in which case the balance is taken from the latest known block. So you got your client, you call balance at, you give it an address, you give it a block number. If you leave this nothing, it will just check the latest block. Call context, eth.get balance, underscore get balance. Storage at returns the value of the key in the contract storage of a given account. Block number can be nil. So you do that on all accounts. They got balances. Contracts also have storage, so you can get the storage. That's a bit interesting. So this is actually coming to the more like useful functions now. So you got an address, and you want to know the code that's there for the address. So you call code at, or you want to know the storage. This is going to give you bytes, which is hard to work with. It's got the nonce. So these are the 4 things that are in an account state, I believe. So Ethereum, yellow paper. Use state. Block state. Cool. So the account state comprises of these following 4 fields from the yellow paper: a nonce, a balance, storage root, and a code hash. So these are hashes, but they point at something else. So you can get the storage, you can get the code, you get the nonce, you can get the balance. So these are giving you all the state. And it says right here, state access. Filters. So if you want to go through the logs, they've got filter queries, which are relatively new to me, but I imagine it would be the same as a MySQL query. but whatever their proprietary thing is. So you've got your client and you make a filter query, and the filter query goes through the transactions and gets the logs. And I think in here, event logs, reading event logs. So yeah, smart contracts may optionally emit events which get stored as logs as part of the transaction receipt. Reading these events is pretty simple. You need to construct a filter query. You import the filter query struct from the package and initialize it with filter options. So from block to block addresses. The next step is to call filter logs. Is that what we've been looking at? Yes, we have. Context.background being blank, and you pass this query. All the logs will be ABI encoded, so by themselves they won't be very readable. In order, we need to import our smart contract ABI. So you got the ABI from the contract stored somewhere, and then you can read it. Cool. So filter query ethereum.filter query. Let's do a quick go-ethererum. Mobile Ethereum, Ethclient filter query, Eth filters. Filter query interfaces.go. Might be in interfaces, which describes the filter query. And it's looking like it right now. Simulated backend. Nope. So where is that? Interfaces.go. So we go up to the very base. Interfaces.go. Package Ethereum. Subscription interface. Chain reader interface. Transaction reader interface. Pending state. Log filterer. Filter query contains options for contract log filtering. Interesting place they've put it. It's got a block hash. Returns logs only from block with this hash. So if you only want to look at the logs from one block, you can pass block hash. Or you can do from and to. It gives you the range of blocks to look at. Addresses. So you pass an array of addresses, which are the contracts you want to look at. The topics list restricts matches to particular event topics. So if your contract has many events, you can filter to certain topics. There's a little bit more to it actually. You've got to set what the topics are in your contract, I believe, but you can have an array of common hashes. Nil matches any topic list. Matches A in the first position. Matches any topic in the first position, B in the second position. Cool, I don't understand that at all. I don't know what the topics are. But it's interesting that that's there, because when I look at the actual Solidity stuff later on, it'll be a bit more useful knowing that this topics is how they filter it. Cool. Back into Ethclient. Filter logs. e.ethereum. Q is ethereum.filter query. Subscribe filter logs is the same thing, but it makes a subscription, so it actually listens. So whenever your node makes a new or picks up a new block, any of the filters that are set here will be returned in this channel. Then they get a function that's toFilterArgument. Returns an interface and takes a filter query. Map string interface. To block from block address and topics. So this is interesting because it feels like it takes a filter query. These are all using filter queries anyway. And it's returning an interface, which is the same thing, I would imagine. Or it's just stripping away the filter query. Who knows? Pending state. So when something hasn't been finalized, but you got transactions in your pool that are waiting to go, I believe pending balance will tell you to balance after all these transactions have been taken into account and not just what's on the blockchain. So pending balance at account address. eth.getBalance, and they pass this pending. So if we go up a little bit, they were calling getBalance in this other function. Somewhere. Headed by number. And they call toBlockArgument. So you can pass, to this call context, you can pass a block num_arg, which takes a block number. Oh, your block number is an integer, and then this takes a string. That makes more sense. A hex string gets passed to call context, and that's what this other function down here was doing. To block num_arg. Yep, cool. Anyway, or you can call pending. So it's a hex string of the number, or it's pending. Pending storage at, pending code at, pending nonce at. Pending transaction count. To do subscribe pending transactions needs server side. Interesting. Contract call in. Call contract executes a message call transaction, which is directly executed in the virtual machine of the node, but never mind in the blockchain. So the block Ethereum makes this big difference between calls and transactions. So you can use functions on a smart contract for free if you're calling it. And essentially what it means is your computer runs the code on itself and it doesn't need anything else. Or you can submit a transaction which modifies the state.